In the Italian site of 5Growth, Comau, Ericsson, TIM, Politecnico di Torino, Scuola Superiore Sant'Anna and NextWorks are deploying a joint pilot to experiment key enablers for the factory of the future. This video illustrates the digital twin-up use case deployments realized in November 2020. The Comau pilot architecture includes a private 5G radio network operating on the TIM spectrum, which offers 5G connectivity to robots, types of machinery, sensors, and devices. The radio network leverages on transport infrastructure based on an optical fiber ring with add and drop multiplexers coupled with electrical switches. An orchestration system, a key component of the 5Growth platform, oversees the radio, transport, and cloud resources automation. It is capable of setting up and operate each vertical service. The first use case deployed in the Comau pilot is the digital twin-up solution. Here, a 5G connected industrial robot Racer 3 receives a predetermined sequence of commands from a computer connected to the same 5G network. The robot controller, which runs the motion control function, is co-located with the robot. The controller executes the commands received from the computer and estimates the actual positions of the robot via the encoders installed on the access motors. Through the low-latency 5G links, these positions are continuously sent back to the computer, which builds a real-time digital twin of the Racer 3 robot through a specific software module. The digital replica will be used to feed the augmented reality headset to be used by a human supervisor. The perfect synchronized alignment between the real robot and its digital replica is possible if the round-trip latency between these two elements is lower than 15 milliseconds. This value is assumed as a performance target for the 5G network serving the use case. This picture shows the area where the pilot is deployed. It is hosted in the automation system and robotics floors of Comau in Turin. The Ericsson 5G antenna is installed on a pole located in the center of the experimental area. This picture is a zoom on the antenna operating at the frequency of 3.7 GHz on a spectrum licensed by TIM. Both baseband and radio core systems are located on Comau premises to keep the latency low and preserve vertical data confidentiality. This view captures the lab's perspective where the systems constituting the optical-based transport infrastructure are deployed and tested with oscilloscope and the other instruments. This lab is also used for the deployment of components of 5Growth platform. Full integration with Mobile in Comau premises is planned within March 2021. This orientation map locates all the mentioned areas and systems on the architectural scheme. All 4 pilots in 5Growth have a common approach to validate the key performance indicators of the services associated with each use case. For this purpose, specific UC service KPIs have been identified. Each UC service KPI is then associated with one of the 5Growth service KPIs. These are the qualitative indicators defined at the project level that allow validating a business and industrial scenario from the vertical point of view. Finally, the 5 growth service KPIs are mapped on a set of core KPIs, which are the entities on which measurements are done to test and assess qualifying performance parameters. In the digital twin app use case, the service KPIs are related to the expected delays experienced between the robot and its twin, the support of industrial protocols over 5G, and the level of cellular coverage achieved in the shop floor. The related core KPIs mainly targets the end-to-end latency of the wireless connection, the associated data rate, and the packet loss level. Deliverable D4.2 reports all the details on the KPIs and the validation procedures in place. The digital twin app use case requires an end-to-end latency lower than 15 milliseconds to achieve the perfect alignment of movements between the real robot and its digital replica. This latency level is achieved in the pilot by using the ultra-reliable low-latency communications profile of the 5G network. A test campaign has been conducted to measure the latency of a 5G link, which is composed by the radio layer and by the underlying transport layer. As for the radio contributions, results demonstrate an average downlink latency of 5.38 milliseconds at a data rate of 844 megabit per second and an average uplink latency of 6.07 milliseconds at 61 megabit per second. The cumulated end-to-end radio latency is 11.45 milliseconds, well below the target of 15 milliseconds. The radio latency increases with the bit rate as the scheduler must handle a greater rate of packets. So the trade-off between the bit rate and latency is tunable to serve each use case with the most appropriate performances. Further tests have been conducted over a fiber ring of 8.8 kilometers to measure the transport contribution to the overall end-to-end latency. The test methodology was based on RFC 2544. Results demonstrate that the delay introduced by the transport layer is 44 microseconds, about 2 orders of magnitude below the radio one. As a result, the latency contribution introduced by the transport layer is negligible in the overall end-to-end latency. The Racer 3 robot can be manually driven by a dedicated application installed on a tablet. With the app, it's possible to manage all the robot movements, sending commands one by one, through an easy and intuitive graphical user interface. In the digital twin app use case, this process is automatic by using a computer that instructs the robot through a predefined sequence of actions. This video shows the actual demonstration operating in the Comau area, covered by the 5G radio network. It's possible to appreciate the real robot on the right side and its digital replica on the left side. As explained, synchronized movements are possible thanks to a continuous flow of data, without delays, between the robot controller and the computer running the digital twin app. The next step, currently under deployment, will enable the use of augmented reality in the use case with the HoloLens headset.